All right, today we're going to continue section or chapter 2, and this is 2.3. We're going to continue talking about sets, and today we're going to talk about operations and properties of sets. And to start with, we're going to look at some of the different operations on sets. So the first one is called a set intersection. So an intersection is just like when you talk about a street intersection. So the intersection of the street is what? When you talk about a street intersection, where they cross each other, right? So the intersection of the street is actually where the streets cross, okay? So, and when you talk about this specifically, the intersection itself literally is the part in the middle of the crossing of two streets. So Brahms is at the corner of the intersection, but not in the intersection out here, right, on the corner of Hickman and MacArthur, okay? So when we're talking about the intersection, we want something that is common, the set of elements common to both sets. So it has to be on both streets to be in the intersection, right? And we have notation for this, set intersection notation. So if we have two sets A and B, and when I would talk about them intersecting, the symbol is an upside down, like a horseshoe or a U shape. Okay. And set notation wise, we talked about some set notations last time. This is the curly brace that we used. This is our X such that, so this means all X such that. And then X has to be both an element of A and X is an element of B. It has to be in both in order to be in an intersection. Okay, now the union is different. It doesn't make sense to talk about the union of two streets. Okay, so I'm going to talk about union in a different way. So whenever I think about union, I think about the wedding ceremony. Okay, the union and the two shall become one, right? So what does that mean? Well, it means that all that you have is mine and all that I have is yours, right? You get everything. Okay, so you get all the bills, and you get all the savings accounts, and you get all the children of the other person. You get it all. Okay? It all becomes yours as a combined couple. There is no yours and mine anymore. It's all ours. Okay? That's a union. So it has to be in one set or the other. And it could already be in both, and that's fine. But it has to be in one or the other to be in the union. The union symbol actually looks like a U. Okay, so the union of two sets is defined set-wise to be the set of all X such that X is in A or X is in B. One or the other or both, because by both it would actually be in one and in the other by both. Okay? And the last one, relative complement, or difference, is the set of all elements in one set that are not in the other one. Okay? So when we do this one, it looks like a subtraction problem, hence the phrase difference. Okay? And what we do is we get all of the elements that are in the first set. Oops, that was supposed to be A. So they're in A, but they're not in B. Okay, so this is an and. The element is not in B. Now we've talked last time, I think it was last time, we looked a little bit at Venn diagrams. I'm going to draw a Venn diagram picture for each one of these. Just so that you can see a few of the tools of the smartboard for one, and also have a visual picture of what each of these is describing, because sometimes that helps. So on the smartboard, we're going to draw a rectangle up here, and inside of my rectangle I want to draw a couple circles. A circle for A, and a circle for B. Well, that's not going to work. So this one's going to be the universal set, U. We talked about that last time. This will be set A and this will be set B. If you're looking at the intersection, you're talking about what is in both of them. Where is that on this picture? Very middle of that too, that little bitty space right here, right? So when we talk about intersection in terms of a visual picture, this is the image you should have in your mind. Okay? This image of the two streets intersecting, in this case the two circles intersecting. All right, we're going to do this same picture again. Down here. This differently than last time. There we go. All right, so this is set A again, set B, the universal set. And now I want the union. So what part of this picture is the union describing? Yeah, so by both, what do you mean? Okay, so we want the part that's in circle A, the part that's in the outside on circle B, and the part that's in the middle of the intersection. So we need to include all of it. So we get the part over here in A, we get the part in the middle, and we get the part in B. Is that okay? So the union is much bigger than an intersection, right? Much bigger. And our last one down here is the relative complement. Okay, so on this one, I'm supposed to be shading in the part that's inside of circle A and not inside of circle B. Where is that? Just that outer part of A, right? So it's over here. So we have to be inside of circle A, which we are, and we have to be outside of circle B, which we are. So that's a relative complement or difference. And what we're going to do next is we're going to actually do a problem with some context on how this sort of works out. And the context is going to actually be a blended family, okay? So we have consider Mary, single mom of one child, Mark, and Joe. Oh yeah, I haven't typed on my slide. Maybe it's fixed on yours, you'll have to tell me. Yeah, it's wrong on the board anyway. Okay, Mary, single mom of one child, Mark, Joe, single dad of two children, Jack and Jill. It should say Mary and Joe get married. Not be good for Mary to marry Mark. No, no, no. All right. I remember when I did that one last time. That's how definitely didn't get fixed. Okay. So Mary and Joe get married. Together they have two children, Ann and Andy. M is Mary's kids, J is Joe's kids, and we're going to find the following. Okay. So what are we going to find? Well, first thing we're going to find is we're going to find the intersection. Then we're going to find the union, and then we're going to find the relative difference, or the relative complement of the difference. Okay, so to start with, Mary intersect Joe. What in the world do we have when this goes on? Who is in Mary intersect Joe? Ann and Andy. So this has to be the children, the description of what we're finding is we're finding the children that are common to both parents, right? Okay, and that was described as the Ann and Andy after they get married. What is the union describing in this situation? All the kids. The union is the family picture, right? It's who gets to be in the family picture, as long as nobody's, like on the outs with mom or dad. They're all going to be in the union, in the picture, in the Christmas card picture. Okay, so we want all the kids. That's what we're describing as the union. So we have who? Mark, Jack, Jill, Ann, and Andy. And then what is this describing? M minus J. What in the world does that describe? It describes Mark. So specifically in words like description-wise, what is it describing?
Only like Mary's child.
Yeah, so this would be Mary's child, not with Joe, right? Mary's children before Joe. Okay, so this would be Mark in this case. And it's important to realize, we'll put another one in here, that this is different than this, isn't it? If we did Joe's children minus Mary's children, this is not going to be the same group of kids. Who would this include?
Jill.
This would include Jack and Jill. Okay? Now, this is an interesting feature because if you had done that on part A and switched them, or on part B and switched them, what would happen? It's the same group of kids, right? But when you switch to the relative complement, it does change the group of people that we're talking about. All right. And that's exactly what this slide is talking about, is commutativity. So if you're talking about unions or intersections, there is commutativity going on. That is, if I do A intersect B, it's the same thing as B intersect A. Think about that. You know that about intersections of streets, right? If I talk about where Union and, well, let's use MacArthur and Kickapoo. If I talk about MacArthur and Kickapoo crossing, or I talk about Kickapoo and MacArthur crossing, it's the same crossing, it's the same intersection, right? Doesn't matter which order I say it in. And if I talk about, whoops, again, we'll use my marriage example, the union of Joe and Mary. If I talk about the union of Joe and Mary's kids, or the union of Mary and Joe's kids, it's the same kids. It doesn't matter what order I do them in. And this works for all sets. A and B. So it doesn't matter if I'm talking about streets or if I'm talking about kids and parents. It doesn't matter what the context is, this is going to work. There's also an associativity in these ideas. So in other words, you've seen the associative property. The associative property has parentheses, that's what usually people remember. It's what we associate together. So if I have the union of B union C, right, and then I union that with A, it would be the same as doing the union of A and B first, and then doing the union of that with C. It doesn't matter what order I do it in. Okay, if I associate any two of those together and then I associate the third one with it, it's the same association. And the same thing happens when I do intersections. If I do the intersection of B and C, and then intersect that with A, that'll be the same thing as doing the intersection of A and B, and then intersecting that afterwards with C. Again, the association doesn't matter, the grouping doesn't matter. I get the same group of people or sets or picture any way I do it. Perhaps the most interesting is the distribution. So the distribution, when we do distribution with whole numbers or real numbers, and we're looking at distribution, we're talking about what set operations, what arithmetic operations, do you remember? When you remember the distributive property, what do you remember? Multiplication, that's one of them. You should remember it as multiplication over addition. So it looks something like that on one side, and then it ends up being AB plus AC on the other side. So you either had addition or subtraction, you have subtraction inside the parentheses, and you get this multiplication feature over the addition or the subtraction. Sort of ringing bells. We're going to talk more about this far later, but it's something you've seen before. And the same thing happens when we do distribution for intersections over sets. So we've got a intersection here on the outside, and we're going to have a union on the inside. And this is actually the same as doing the intersection of each of these individually. So A intersect B, and A intersect C, and then doing the union. It looks just like what happens over there in the addition and multiplication distribution that we see before. Do you see it? What we have here is we have the intersection of each of these individually, whereas we have the multiplication of each of those individually, and we have that same operation, which in our case is union between them, and over on the other one was addition between them. And what we're going to do next is we're going to work a little bit with some Venn diagrams to talk about how to look for the portions of the diagrams that these intersections and unions are referring to. Oops, did I skip one? Oh, I'm one ahead of me. Okay, I'm sorry. We're going to do cardinal number first, then we're going to do Venn diagrams. Okay, cardinal number formula, I'm sorry. Cardinal number formula talks about how we count how many items are in a particular set. We talked about cardinal numbers last time. Do you remember? What does cardinal number mean? If I asked you to find the cardinal number of set A, what am I asking you to find? Somebody say it. The total number in set A, right? It's just counting how many items are in the set. So we're doing the same thing here, but we're going to be doing it for a union. So if you're counting the number of items in the union, picture-wise, so the picture we had was the second picture from before, right? What did the picture include? What was shaded in? Right, the outside of A, the outside of B, and the middle part in the middle, right? Okay. Well, the problem is that if you count how many things are inside of set A, and if you count how many things are inside of set B, you have a problem. So let me show you what I mean by that. So let's take that picture again. That's what I wanted. All right, so I had my set A, my set B, and my universal set. If I count the number of items in set A, in essence, I'm counting everything in the red circle, right? That is the number of items in A. So it's the area inside of A. And if I count the number of items, or I shade the area inside of circle B, I get this. And what inherent problem did I create? I did. I counted the middle twice. Because I shaded it twice. So whatever was in the middle got counted or shaded twice. So in the cardinal number formula, the piece that's missing is actually we subtract off the intersection because we counted it twice. It gets counted when I counted circle A, it gets counted when I counted circle B. So I subtract off the part where it overlapped. Okay? What you have to remember is that this NA does not mean the outer part of A, it means the entire circle A. Yes?
Is the sign before the last one where it's subtracting it, is that the number or is that the
This N right here means number. Yeah, so when you have the N before something, it means the number of items somewhere gets subtracted off. And
I got other things.
like a capital N? If you
Or
like,
is that
it's okay. Your book uses a
because
lower
it
case.
kind of looks like
Oh, it looks like the intersection.
I mean, like, I just think, like, I would probably
Yeah,
write
it's
it.
fine if you use lowercase. Your book uses lowercase. I can use that. Yeah, so that means number. That N on the outside of those symbols means number of items. All right, there's one other set operation here, and this is Cartesian product. All right, so the Cartesian product is the set of all ordered pairs where the first component comes from the first set and the second component comes from the second set. So let me show you how this works. Okay, so let's say that we have A cross B, and this is what this looks like. The Cartesian product is A cross B. And I need to call these sets something, so I'm going to say that set A has items A, B, and C in it, okay? And set B has items 1, 2, 3, and 4 in it. I've got two sets. What I'm going to do is I'm going to create ordered pairs, right? So my set with my ordered pairs looks like this. I do ordered pairs, which are inside of parentheses, just like in the XY ordered pairs that you've seen back in algebra, okay? The first component has to come from set A. Well, I have a little a in set A. The second component has to come from set B. I have a 1 in set B. So the ordered pair A1 is going to be a part of this Cartesian product. Okay? But I didn't have to group letter A with the number 1. I could have put letter A with the number 2. This is another element inside of the Cartesian product. I could have put the letter A with the number 3, or the letter A with the number 4. I'm just doing all the possible groupings that there are, right? But that is all of the ways that A can be grouped with anything in B. Agreed? So I've exhausted all possibilities for A with a number. But this is not my whole set. What am I missing? B and C. So I can do the same thing with B that I just did with A. I can do B with 1, B with 2, B with 3, or B with 4. Or I could do C with 1, C with 2, C with 3, or C with 4? This is something akin to how many pairings could you possibly have in the classroom if you had 3 girls and 4 boys, right? And how many did you count? I mean, how many of them are in there? There's actually 12 of them in there, and this is a really interesting feature. So if you were to count, that is, you wanted to know the cardinality of A cross B, you actually found out how many are in this particular one. 12. Because there's 12 of these guys, right? But how many were in set A? There are 3, so N of A was actually 3. And how many were in B? 4. And if you can use your imagination, how could you use 3 and 4 to get 12? Multiply them. So there's actually another cardinal number formula for cross products, or I'm sorry, Cartesian products, that says that N of A cross B, I'm probably doing something out of order, this is maybe on a slide later, I don't remember, is N of A times N of B. And it worked. I mean, we saw it work for this specific example of 3 and 2, 3 and 4, right? Where works that had 3 items, which that had 4 items. But it works for any number of items. Excellent. Okay, let's do a couple of examples before we pause. All right, we're going to use Venn diagrams to shade the following sets. And the first set we're going to shade is this one. So we encountered this notation last time. This notation with the single bar on the top of it, what does it mean? Complement. And what does complement mean? The opposite. So if I talk about the set A, what does complement mean? Not in A. Okay, so it means something that's not in that set. That's what complement means. It's not a part of that. All right, this one actually has 2 sets listed, set A and set B. So in drawing my Venn diagram, I need to have a set, or I need to have a diagram that has how many circles in it? 2. Okay, so you've got 2 circles rather, inside of a Venn diagram, A, B, and U. This is what you do first. Now, what I'm about to show you is what I expect to see every single time you do a Venn diagram. Everybody clear on that? Okay. So if you don't show me the pieces that I'm about to show you, that's equivalent to not showing work. All right. There are other ways to do this, and I recognize that fact. But what I'm about to show you works all the time, and it's a very organized way to make sure you don't make a mistake in doing it, which is really nice. So what we're going to do is we're going to label each of the regions of this picture. I tend to start inside of circle A. It doesn't matter, though, if you don't want to start there. You can start somewhere else. And there are 4 parts of this picture. The outer part of A, the intersection, the outer part of B, and then the outer part of both circles, which is inside of the U on the outside. Everybody good so far? Excellent. What we're going to do next is we're going to identify which of the numbers are in each of the pieces of this. A complement. What numbers are in A complement? 3 and 4. Remember, it means outside of circle A. And there are 2 numbers, 3 and 4, outside of circle A. And we're going to do the same thing with circle B. But we're finding the complement on that one too. So what is the complement of B? That's 1 and 4. And then this says that I'm supposed to take each of these sets and I'm supposed to find their union. What does union mean? It means what? Did Hannah or Angela, what did you guys say? What's in both? What do you mean by both?
What's in set? Wait.
See, we use the word both, unfortunately, in this case. So I want to be real clear. Do you have an idea, Carrie?
I was just gonna say like put them together.
So what do you mean by put them together?
Put the 2.
Here, let me do it this way. What would you like for your answer to be, Carrie?
1, 3, and 4.
1, 3, and 4. Okay, that's correct. So union means I get everything. Right? Union is that marriage idea. I get everything that's included everywhere. Okay? So I get 1, 3, and 4. And I have to remember what the directions actually asked us to do. Shade. So you actually have to shade. So it has students who do all the work and then they don't give me the answer. The answer is the shading. So I need to go back and shade the circle, or the parts of the circle where 1 is, where 3 is, and in this case also where 4 is. Okay, is everybody with me on that one? Okay. All right, let's do part B here. All right, so part B is going to look a little bit different. And you're going to tell me why after I write it up here. What is different about part B? There are going to be 3 circles because I have 3 different identifiable letters, right? A, B, and C. And so when I draw this picture, I need to draw 3 overlapping circles. And they look something like that. So it starts to look a little bit like those Olympic rings, right? Now the process works the same way. I need to put numbers in the different regions. I just have more regions now. I don't have 4 numbers. I'm actually going to have, there are 8. That's right, Hannah. Good. There are 8 different numbers. And like I said, I always start with circle A. It doesn't matter. You can start wherever you'd like. I'm going to start in A, and I go across the top. So 1, 2, 3. I go across the middle. 4, 5, 6. 7s and C and 8s on the outside. If you get your numbers somewhere else, it's fine. Your picture's still going to work with your numbers. Your picture will match mine when you're done. Okay? Again, the process works the same way, except that what else do you see on this particular problem? Because there are 3 of them. There is an intersection. There's also a union. What else do you see? I don't need the distributed property. I could use it, but I don't have to have it. Okay, let me try it this way. Where do I start on this problem? The parentheses. I actually have parentheses in this problem, right? And just like with algebra, parentheses tell you where to start. You have to start with what's inside the parentheses. That's your starting spot. So the first thing I'm going to start with is A and B. And I don't have any complements on this one, so I don't have to worry about that. What numbers are inside of the circle representing the regions inside of circle A? 1, 2, 4, and 5. How about inside of circle B? 2, 3, 5, and 6. Okay? Now, that's not the only thing that happens inside the parentheses. The inside of the parentheses also relates A and B together with what operation? Intersection, right? This says I need the intersection. And what does intersection mean? The ones that they both have. And so what do you mean by both? What they have in common. Common is the word I always use too. So the pieces they have in common. So what's in common to both sets? 2 and 5. So the intersection is simply 2, 5. Now I've done everything inside the parentheses, so I'm going to move outside the parentheses. I have another set. I have the set C. So what items or numbers are inside of set C? 4, 5, 6, and 7. What am I supposed to do next? I mean, I'm supposed to somehow combine these two. How do I combine them? What's it say? This one says union, doesn't it? So I'm supposed to say take this set that's A intersect B, which was 2, 5, and I'm supposed to do the union with set C, which was 4, 5, 6, 7. What does union mean? It means everything. You get everything. So, Kristen, what do I get here?
2, 4, 5, 6.
I get 2, 4, 5, 6, and 7, and then back in my picture I shade every region that I just listed. I shade region 2, region 4, region 5, region 6, and region 7. Okay, let me make a comment about this one. We're going to pause here. We'll pick back up next time. The comment I want to make on your shading about this stuff is your shading needs to be obvious. What do I mean by that? Well, unfortunately, what happened when I just wrote over my shading is you don't see my numbers underneath very well anymore, do you? make sure I can still see your numbers reshaped, so that I can know if you did alter your numbering that it didn't mess things up. Okay? I want to be able to see what your numbers actually were. So shade light enough that I can tell you shade. I mean, dark enough I can tell you shaded, but light enough that I can still see your numbers. Okay. All right. Yes.
Do you have to start out with like listing A and B, or can you just go ahead and start with intersection?
If you write, like if you did not write this piece right here,
Uh-huh.
and you only wrote this piece,
Right.
as long as you write that piece out for me, that's okay.
Okay.
It's probably gonna be a little more complicated if you had complements included. Like if it said A complement union B, you might find a little more difficulty in looking at it and just saying, oh, I know immediately what that is. You might very well make it be easy mistake just because you chose not to write it out. But on this one, yeah, it wouldn't have been too bad, right?
Right.
Because we already have that picture that we've established in our minds of what that looks like.
Yeah.